In this lecture, we'll do algorithm analysis on our dynamic array and unordered dynamic array classes. We'll start by doing the algorithm analysis for our parent class because that applies to both the unordered and the ordered dynamic arrays. So let's take a look at clear. What is the algorithmic complexity of clear? Well, the only thing it's doing is an assignment, and assignments take constant time. Now remember, constant time doesn't mean zero time. It just means that the amount of time it takes has nothing to do with how many elements are currently in the array. So because we only do one thing that takes constant time, this is order 1. When we do the toString method, we see that we do a for loop over each of the elements in the array. And that means that this for loop executes n times, where n is defined as the number of valid elements in the array. We still need to look inside the loop to make sure there's nothing else that we need to worry about, but append is order 1. And checking a Boolean expression is order 1, and append is order 1. So the entire body of the loop is order 1, or constant time, not zero time, but constant time. So all we care about is this loop that goes n times, and the last line of code converting to the string is also constant time. So the only thing that's dependent on how many valid elements there are in the array is this for loop that executes n times, so the toString operation is order n. Expanding the array is also order n. This is constant time, this is constant time, and this is constant time. But this loop executes n times because we have to copy each of the valid elements from the old array into the new array. So because we have this for loop that executes n times, the expand operation is also order n. In the unordered dynamic array class, adding is an interesting operation. Here's the problem. Evaluating this Boolean expression is constant time. Doing this assignment is constant time. And doing this increment is constant time. But expand, as we just discovered, is order n. So if we don't have to expand, if this Boolean expression evaluates to false, then this is order 1. But if we do have to expand, this is order n. So really, in the worst case, right, the worst case is that we're expanding the dynamic array, so that makes it order n. However, it is very common because as the array gets larger, we need to expand it less often. That's why we're doubling it each time. It turns out that most of the time, this is order 1, except in those cases where we need to expand it, and then it's order n. So worst case is order n, but if you get a chance to describe it a little more, you can say it's order 1 if you don't need to expand the array, and it's order n if you do. There's actually a term in algorithm analysis that lets us say that the add operation is order 1 amortized. And this comes from finance, of course, where we amortize investments over time. So most of the time this is order 1, and then in rare cases it's order n. So there are a variety of ways to address this, but this is a tricky one because the algorithmic complexity of the add operation depends on whether or not we need to expand the array. Luckily, we don't have that problem here in remove, because we'll evaluate index of. I guess we better go evaluate index of now. Index of does a for loop over each of the elements in the array. So in the worst case, we have to look at every single element, and either we find the item we're looking for at the very last location in the array, or we don't find it at all and we come down here. But again, this for loop goes n times. This is constant time, and this is constant time. So the body of the loop is constant time, but the outer loop goes n times. So index of is an order n operation. That means that this line in the remove method is order n. This is constant time. This is constant time. These are each constant time, but this order n call to the index of method at the beginning of the remove method makes remove an order n operation. To recap, in this lecture we got practice doing detailed algorithm analysis on C# source code.